Good afternoon, everybody. This afternoon, we are going to talk about rheology of food materials, principles and applications. Yesterday, we talked about mechanical properties of materials, where we talked about elastic nature of the material, solid material. And this morning, we talked about the viscous nature of the material, viscosity. This afternoon, I like to combine both the elastic and viscous nature of the material. So, it will be viscoelastic properties of the material. That is what we are going to discuss this afternoon. This afternoon session is primarily it's a classic session. It does not talk about dynamic rheology yet, but this is primarily about the combining elastic and viscous nature of the material. So, we all know that any food material you can think, you consider it's a viscoelastic. It's more elastic and less viscous a lot of times. Very seldom it is more viscous and less elastic. Mostly it is viscoelastic, but mostly elastic and viscous. And there are different ways we can approach this. I'm going to explain to you one by one what is the best way to approach this, and then so that you will get a better understanding. So, any food material you take, it has both viscous and elastic properties. When we say elastic, we are talking about the ideal solids. It's a spring component, right? When you apply the force and release the force, it comes back to the original shape, which is a spring component, which is elastic. And then the ideal fluid is a dash part. When I say dash part, it is analogs to the spring component. Spring is elastic, dash part is viscous. So, when you think about the spring, you have a spring, you load the spring, when you unload it, it comes back. All the energy you put in, it's recovered in the elastic component. In the viscous, its dash part, primarily reason is when you apply the force, the piston which is inside the cylinder slowly goes down, and then when you release the force from the dash part, it does not come back. It does not come back at all. When you apply the force in the dash part, it keeps going down, and then when you release it, it does not come back at all. So, whatever energy you put in, everything is lost. Understand? That is a viscous component. Here we are considering material, our food material has both the elastic component and viscous component. It's a consideration only. It's not actually, we don't know how many springs are there, how many dash parts there in a given material, food material. We do not know. It's all hypothetical case. We try to understand our food material in a classical sense. That's why we call it, that's why it is viscoelastic. So, it's a component of steel which is elastic, pure ideal solid, water, it's ideal fluid. Not only water, oil, any Newtonian fluid, those are all ideal fluid. They do not have any elastic component. Follow me? Because any material you take, we have a lot of carbohydrate, protein, fat and things like that, moisture. So, fat and moisture correspond to viscous component, carbohydrate, protein, other things correspond to elastic component. That's way to look at it. That's one way to understand why it is viscoelastic nature. Biological material are viscoelastic. So, how do you compare this? So, if you consider elasticity, if this is stress over strain, you get modulus of elasticity, right? That is elastic component. Viscous component, you have shear stress, shear rate, slope is viscosity. This is eta or mu. You can call it any way you want to call it. This is elastic component, this is viscous component. Joined together is viscoelasticity, and that's what our material is all about. Is everybody with me? I mean, you understand why we are doing this? This is how we, because it's any food material you can think of, everything is viscoelastic. They cannot be purely elastic, they cannot purely viscous, except for the purely viscous component. One more thing is, elastic component, energy you put in, you can recover back. Everything will come back. Viscous component, energy you put in, nothing comes back. But in actual food material, some energy is coming back, some energy is lost. Right? That's what we discussed yesterday also, where we have loading and unloading section. In fact, when we do the TPA, after this discussion session, when you go to lab, you will see that when you do double bite, even single bite itself, you will know that some energy is lost and some energy is recovered back. Whatever energy lost is due to dashpot component. Whatever energy regained is due to the elastic component. Otherwise, if it is purely elastic, whatever energy you put in, you have to get back. If it is viscous component, whatever energy you put in, you won't get anything back. Make sense? Okay. So that is a classic nature of the material itself, and that is how we are going to analyze it. So elasticity, stress is a function of strain. Viscosity, stress is a function of strain rate or shear rate. The slope is modulus of velocity for elasticity, and the proportionality constant is viscosity for the viscous component. Elasticity is based on Cook's law, viscosity is based on Newton's law. Here stress is independent of strain rate, because it's only stress and strain, there is no rate in the elasticity component. In the viscosity component, stress is independent on strain, stress is independent on strain, but stress is dependent on the strain rate. In elasticity, it is time independent. Elasticity doesn't have any component, time component is not there, it's in time independent. In the viscosity, this can be time dependent or time independent. For our practical purposes, we are going to think about the both the time dependent and time independent also. Here, if you look at the stress and strain elasticity component, because stress is independent of strain rate, so you get what you get is it's both the strain rate and strain rate 2, elasticity and viscous component is everything is included within the elastic component itself. This is for viscosity, stress over shear strain rate, slope of the line is viscosity, and when you combine, this is spring component, this is dashpot component. When you combine these together, which is viscoelasticity, and then when you study them as a function of shear stress and strain, then as shear rate increases, strain rate increases. So with the increasing strain rate, you will have the different component of the stress over strain. Okay. Classic example, you consider either your foot material has one spring and one dashpot. Okay. If you have a spring, one dashpot, either you can connect them parallelly or you can connect them series, one after another, that is series, parallelly next to each other. We don't know actual foot material how it is connected, but there are two simple cases we can consider where material is suddenly loaded and held at a constant stress, and then you monitor the strain over time. So it is creep up, or in other words, less force is required for the same deformation. So it's a step stress, and that's why it's called creep. It's creeping up. So when they are connected to parallelly, it is creep. If they are connected seriously, that's called the relaxation, stress relaxation. So stress is instantly applied, held constant, and then you monitor the strain. So when you monitor the strain, if it is ideal elastic, complete recovery, no loss. So whatever you apply, the strain will be always constant. And then ideal viscous, it's a steady flow, no recovery. Whatever energy you put in, it get lost. But our material is viscoelastic, so there will be a permanent deformation where the energy, some of the energy you applied, lost for a viscoelastic material. And this is ideal case for the creep behavior. Stress relaxation, on the other hand, material is suddenly deformed. You deform it and you held constant strain, then you monitor the stress decay. Stress over time will decay, less force required for the same deformation. So in this case, what you do is you apply the strain, constant strain, then you monitor the stress. If it is ideal elastic, stress is also constant because stress is proportional to strain. Whatever strain you apply, corresponding stress you will get it. So ideal elastic is constant stress. Ideal viscous, there is no stress at all. Because when you apply it, there is no stress at all, ideal viscous. But our material is, if it is viscoelastic liquid, the stress will decay like that and it will go to zero. If it is viscoelastic solid, then the stress will decay and there will be a permanent loss of stress or loss of energy. That's what will happen with the viscoelastic solid. Because any food material you take, they are viscoelastic. And there are two cases you can look at it, very simple cases. One component, one elastic component, one viscous component. Elastic is all about spring, viscous is all about dashpot. So there are only two cases you can look at it. Either they are connected parallelly, which is a creep, or they are connected series. If you consider only one spring and one dashpot. That is a simple case scenario, right? In actuality, your food material may have many springs, many dashpot. We don't know how many springs and how many dashpot will be there. And that's why there is a lot of combination of number of spring, number of dashpots are there. So it all depends upon how well you want to model your food material. If your food material is more liquid, less solid, then that is considered viscoelastic liquid. If your food material is more solid and less viscous, then it is considered viscoelastic solid. On the other hand, if you apply the constant strain, constant deformation for your food material, and then you monitor the stress relaxation, if during the monitoring of stress relaxation, at the end of the process, if your stress is zero, then that material is viscoelastic liquid. On the other hand, your material goes down and the stress is relaxed, but there is a residual stress left at the end of the process. That's called viscoelastic solid. Because it has more elasticity and more viscous. And let me think about that. So it has some viscous component, more elastic. So there is some things lost. This one has more viscous, less elastic. So more viscous means everything is lost. You are not getting it back. The viscoelastic solid, it has more elastic component. So that's why the stress relaxation is it doesn't go to 0. This has more liquid, so that's why it goes to 0. Okay, so what is the mechanical analogs? Solid is spring, liquid is dashpot. That is the mechanical analogs, and this is how we are going to describe it moving forward. There is a spring component, there is a dashpot component, and for viscoelastic models, spring is dictating the ideal elastic element, and dashpot is describing the ideal viscous component. So they can be placed in series or parallel with the other elements. So there are two people described this phenomena. Maxwell was the person who said solid and liquid will go series. So this is spring, this is dashpot. They will go next to each other, one below the other one. That's called stress relaxation. And then Kevin Wagit Kevin said they will go parallelly, and that's the creep model. One is stress relaxation, other one is creep model. Spring and dashpot, Maxwell model. Spring and dashpot next to each other parallel, that's called Wagit Kevin or Kevin Wagit model. Because there are two researchers, they describe the viscoelastic material as spring and dashpot in parallel. I don't know which one came first or which one came next, doesn't matter. Somebody did the one and the other person thought, okay, why this way? This can be this way too. But in reality, this is a simple case scenario. But in reality, your foot material can have multiple spring, many spring component, many dashpot component, and they can be put together any way you can dream about it, visualize about it, doesn't matter. But only matter of the fact of the matter is here is whatever way you put together, you have to start analyzing one by one. Because depending upon how your material is behaving, you can put as many models you want and then make it as perfect as possible. One simple case scenario I'll tell you. If it is a Newtonian fluid, very straightforward, right? It's a straightforward thing, stress with respect to shear rate, it's going to be linear, you get one viscosity number, Newtonian fluid, okay? Non-Newtonian fluid, that's not the case. Make sense? So when you combine the spring and dashpot together, elastic and viscous component together, we do not know how many dashpot, how many spring your material will hold. So depending upon how accurate you want to model your foot material, that many components you need to include. Whenever you do a lot of experiments, when you collect some independent variable, dependent variable, simple case scenario is Y is equal to mx plus c, right? That is simple case scenario. Sometimes when you try to model it, not all your data will may behave like this, right? You end up doing the polynomial equation, right? So y is equal to a plus bx plus cx square plus dx cube plus e to the power n, and also the, it's not only x, it could be another components, exponentials, multiplication, division. Yeah, exactly. So it can keep on going that until it become 100% perfect. Same case scenario could be like that here also. So, but we are going to discuss only in terms of the simple case scenario. Either it is Maxwell model or Kevin-Waggett model or Waggett-Kevin model. I don't know who came first, but alphabetically it's Kevin and Waggett model. That's what happens, right? When you have 2 or 3 researchers working on one project, when it comes to publication, sometimes there could be some argument who will be the senior author, who will be the last author, right? Lot of times people compromise. If somebody initiated and they put a lot of time into it, they get senior authorship. Sometimes professor will come saying that your writing is very poor, you don't know how to write, even though you collected the data. I will write the paper, I am the senior author because I am the one who I am the one who was able to publish it, even though you had a data, but I will give you some credit, so you can be the second author or third author. Things can happen like that. Okay? We don't fight it out, right? We just say, okay, whatever professors say, we just accept that because sometimes we think that it's not worth fighting it out, right? Because if we cannot write our own results very well, then there is a compromise. Somebody is doing that, it's okay. At least I get some credit, right? So spring is elastic, dashpot is viscous, and that's what we are going to discuss one by one now. Any questions so far? It is not as simple as what we think it is because food is very complex material. I wish it is an elastic component or viscous component. If it is only a elastic component or only viscous thing, we need varieties. So we cannot really just live with only water, right? How long can live with water only? Only some time. Few days only, right? We need other components also, other energy things, carbohydrate, protein, fat, minerals, vitamins, because our body needs those kind of energy component, right? I mean, if you want to live, you need to consume those things, right? And that's what complicates everything. So food is a very complex thing compared to any other material. Hey, when you connect them in series, it's Maxwell. When you connect them parallel, it's Kevin-Waggett model. When you connect them in series, that's called stress relaxation, meaning that you are deforming the material and then keeping it there, and the stress is going to relax when you do that. In parallel, you apply the constant force, and then you are going to follow the creeping behavior, how the deformation is slowly going to go down. When you have deformation, when you have in parallel model, what happens is it's a creep behavior, which is the you are going to apply the force, constant force, and you are going to follow the deformation. That's what is happening in the Kevin-Waggett model, which is the creep behavior. So when they are in the parallel, which is creep, Kevin-Waggett model for creep, you apply the constant load. Okay. You cannot do this experiment in your textural analyzer. Remember that, because you have to have your foot is somewhere sitting there, then you need to apply you just need to put some weight there, and then you need to have some type of instrument, uh, transducer or something which can monitor the deformation. The other way to explain is, okay, let's say this is your foot material, you just need to put a weight on top of that. So when you put the constant force here, then you monitor how the deformation is occurring. As soon as you put there, this will not just like that instantly go. It will not. It will slowly go down. So that's what you are monitoring. You are monitoring the deformation with respect to time. That's what the creep is all about. On the other hand, if the foot material has a spring and dashpot, no, not a spring and dashpot in series, where what you do is you constant deformation and then you monitor the stress. Here you are monitoring the strain for a constant force. So when their elements are in parallel, therefore the strain in the spring is equal to strain in dashpot. When you apply the constant load, the dashpot is going to think I would need to go down immediately. It will try to push it down immediately, but the spring will say, you cannot force me like that. I have equal footage here. You have to follow me. Spring will say, I want to go back. Dashpot will say, no, I don't know, I cannot go back. I have to keep going down. And that's what happens when they are in parallel. Follow me? Because that is a typical behavior of the dashpot. When you are forcing it, it will keep going. It will not come back. It will resist. But the spring also hand to hand it's going. So spring will say, no, I have to go back. That is inherent property of myself. I cannot follow you. So even though dashpot will resist, but the spring will govern the strain. That's why the constant strain in both the spring and dashpot, same level. Make sense? This is the only way it can happen. If you connect them like this. So you have a stress over strain. So each one has its own strain rate here. So retarded elastic deformation, where dashpot governs first before spring kicks in over its dashpot, and this is a typical nature you will be getting when you have the spring and dashpot in parallel. So how do we model this? It's a Hookean solid. The maximum strain is achieved immediately in this case. So viscoelastic material, if it is a Hookean solid, pure solid, maximum strain is achieved immediately. But viscoelastic material, there is a particular time to reach maximum maximum strain is retarded. So that is called delta retardation time, which is time required to reach 1 minus 1 over E of the maximum strain. On the other hand, if it is Newtonian fluid, time to reach maximum strain is infinite. Because if you just consider only dashpot, it will not go directly, immediately to the bottom. It will slowly go down. It will not come back. That is the classic nature of the Newtonian fluid. Hookean solid or spring component, when you apply the force, depending upon the spring constant, it will immediately achieve the maximum strain. So when you have a combination of this and this, the time to reach the maximum strain is retarded, so only 63.2% of the maximum strain will be achieved. in creep case, in the case of creep. Okay, let's do an example problem. At least it gives you some idea. So let's assume you have a cylindrical sample which is 20 millimeter diameter. You are applying 200 Newton constant load. So you are putting 200 Newton constant load. The measured strain, so now you have some type of LVDT, linear variable differential transducer, and it's going to measure the deformation or strain over time. So strain is going to keep increasing until it reaches the maximum value. In this case, it's 0.38 strain. That's the maximum strain. Now we want to calculate the retardation time and theoretical viscosity of the material. It's a theoretical viscosity, remember that. It is not actual viscosity because there is no way you can determine the actual viscosity of the solid material. Right? You cannot really absolutely calculate the viscosity of solid material. Only if you do this kind of modeling work, then you can try to measure the theoretical viscosity of the material. So this is your strain over time, it's a creep. So from these you can find the theoretical viscosity. First thing first, you are going to calculate how much is the strain the material will have, which is 63.2% of the maximum strain. So if you calculate the 63.2% of maximum strain, maximum is 0.38, you get 0.24. So you go through this curve, find the 0.24 and then come down, you will get 11 seconds, and that is the retardation time. Retardation time 11 seconds. So once you get the retardation time, then you can go back and calculate the theoretical viscosity. So retardation time is viscosity over modulus of elasticity. So viscosity is modulus of elasticity times retardation time. Modulus of elasticity is nothing but stress over strain. So from force is here, force over area is stress, and we already have a strain, and then times retardation time, then you can calculate the viscosity. So force over A divided by strain times retardation time. So 200 newtons divided by pi r square divided by strain, which is 0.38. So 0.38 is maximum strain times 11 second. The final value is 18.4 megapascal times second. So this 200 newtons divided by pi r square. So pi times 100 millimeter square. So 1 millimeter square is 10 power 6 meter square. Millimeter square cancels. 200 cancels. And then divided by 0.38. And times the 11 second. So if you calculate that, you will get 18.4 Pascal, 18.4 times 10 power 6 Pascal, or 18.4 megapascal. And then this is second, so add the second. Any questions on this example? This is only way you can try to find the theoretical viscosity of this solid material. There is no other way you can find you can measure the viscosity of solid material. Questions? Because this is solid material, you cannot put it in any instrument where you can measure the viscosity. But this is one way you can calculate the theoretical viscosity based on the assumption that this elastic material, this solid material has one spring component, one dashpot component, and they are connected parallelly. I hope you appreciate these calculations. I'm not forcing here anything. I'm just explaining to you how to have some meaningful information from your experimental setup and what does that means. That's what the engineers do, right? As an engineer, we try to design things, and if it works out, great. Otherwise, we go back and change assumptions and come to find a new way of getting the answer. The answer may not be the accurate answer, but at least there will be an answer. It's not a fake answer, but this may not be accurate answer. Any questions? At least you guys can appreciate that there is a way to get this information, right? At least that way it is a great thing, right? I mean, there's no other way you can get it. This is the only way you can get it and have some meaningful information. When we come back at 4 o'clock, I will explain to you how to do the dynamic rheology, where you can do oscillation test instead of doing this compression test. You can do oscillative stress test, where you can get elastic modulus, viscous modulus of this material. But that is again, that's only modulus value, not actual viscosity value. You cannot get viscosity value from that method. You can only get the modulus values, elastic modulus and viscous modulus. And this is only way you can get at least get the theoretical viscosity of the material. Okay, let's look at the Maxwell model for stress relaxation. Here we are assuming that both the spring and dashpot, they are connected in series. They are in series, therefore strain in spring will not be same as strain in dashpot, because dashpot is going to go on its own and spring is going to go on its own. They'll have their own deformation rate because they are connected series. So here dashpot is going to dictate everything. Dashpot will say, I just want to go take my own time, I just want to go slowly. Spring will say, no, I want to go back immediately. That's my characteristic. So, but at the end, the dashpot will absorb the strain, then this will control everything in the whole process. That's what is happening here. Total strain is a combination of spring and dashpot, and then if you take the strain rate, rate of total strain is spring strain rate, dashpot strain rate. Dashpot is nothing but stress over viscosity strain rate. Here it will be the change in stress over the modulus of velocity times the time factor here, delta t. That's what happening with the Maxwell model. So first spring first governs before dashpot becomes the controlling factor, and that's what's happening in the Maxwell model. So stress over strain, then this is the classical spring model, but with the dashpot attached, you get the two different strain rate because they have their own strain rate and they need to accounted for. So similar way you can analyze it. Ideal solids, no relaxation is observed. So relaxation is infinite here, and viscoelastic material relaxation is finite. The ideal liquids, immediate relaxation is 0. So it is infinite to 0, and that's why it is finite. So if you look at the stress relaxation data, because it's a constant deformation, you are following the stress relaxation. So tau relaxation time is the 1 over E, or 36.8% of the initial stress value. And from that you can find the relaxation time, function of viscosity over modulus of elasticity, and you can complete the process. Same thing here we are doing, finding out the theoretical viscosity. Okay, let's look at the example here. There is a constant deformation of 5 millimeters applied, right? Constant deformation, stress relaxation. Cylindrical sample is 20 millimeter. To achieve a strain of 0.1, because 5 millimeter over 20 millimeter, 5 by 20 gives you 0.1 strain. The calculated stress over time is shown here. Determine the relaxation time and theoretical viscosity of the material. So if you look at the initial stress or instantaneous stress, you get 68 Pascal, and then 1 over E, which is 68 Pascal times 36.8%, which is 25 megapascal, 25 Pascal. So you follow 25 Pascal line and then draw a line here. This is your relaxation time, 39 seconds. So once you have the relaxation time, you can calculate the theoretical viscosity. From this equation, relaxation time is equal to viscosity over modulus of elasticity. From there, modulus of elasticity is stress over strain times tau relaxation, similar to what we did before. That is retardation time, this is relaxation time. So 68 Pascal is the stress, the corresponding strain is 0.1, and then you multiply by 39 seconds, which will give you the 26,520 megapascal second, or 0.026 megapascal times second. Okay, I have a last example here, which is going to give you the different answer here. So basically, you apply a constant deformation, 5 mm is applied, it is 15 mm diameter sample, and you are achieving a 0.1 strain. The calculated stress over time is given in this graph. Determine the relaxation time and theoretical viscosity of the material. So we just follow the same process what we did over in this case. So you start with the initial stress, which is the stress relaxation curve 51 Pascal. Then you go to the equilibrium stress, which is 20 Pascal, and from here you get the go back to 51 Pascal times 36.8%, So you get 18.8 Pascal. So you follow the 18.8 Pascal. So the tau relaxation is infinity. It's not even touching that. Because if you go back, so 18.8, so the equilibrium is 20 Pascal, the 18.8 is below that, so it's not even touching that. So that's why your relaxation time is infinity. So your theoretical viscosity will be infinity, because if you multiply this by modulus of elasticity, your viscosity will be infinity. Any questions on this?
So from calculation, the viscosity is infinity, but in like for a theory, but for a practical stuff, how can we say that the viscosity is infinity?
Okay, that's a very good point. The question here is, in theoretical case, when we analyze things like this, your viscosity is infinity. But in actually, how can you say viscosity is infinity? You can definitely say viscosity is infinity because it is keep the equilibrium stress already reached, so this can still keep flowing. It has a viscous component which is very, very small. The dash part is very, very, how can I say this? Dash part is very adamant that I cannot flow much faster than what I am flowing now. So it is going to keep flowing even after we die. That's what it means, right? I mean, it's all about flow. Viscosity is all about flow. Elastic component is all about deformation. So viscous component in this material, solid material, is going to keep flowing, and it will be flowing forever. That's what the infinity means. It can happen, right? I mean, it's a combination of elastic and viscous component, and that's what it is.
So any example of that is where the viscosity
Viscosity is
is infinite?
infinite. There is no material, there is infinite viscosity. We cannot measure it. That's the issue. This is the behavior of the material. Even this morning, madam asked me why this material is shear thinning, why this material is shear thickening. That is the nature of the material. We didn't mean to make.
In reality, there is no existence like this.
There could be this if this material behaves like this, if this material behaves like this, then there is the possibility that viscosity will be infinite. These are all hypothetical case we are trying to explain to you how to better understand the process we are using it, so that you have a better understanding of what you are trying to do. Not relying upon what the computer is going to tell you. It is all about what it is here. Because there is no way we can measure it. That's the bottom line. We know that there is viscous component there because of how the material behaves, right? If this material comes back to the original thing, then we know that it's purely elastic. And we don't want to have foot material which is purely elastic. Correct? If it is purely elastic, we cannot digest that and we cannot live forever. Well, not forever, but however long time, I mean, just think about that. I mean, can we just live with only protein? No, exactly. Yeah, that's a bottom line. If there is only, if we have a food material which has only protein, If we think that that protein is enough for our survival, we cannot, right? So consumer dictates everything. So yesterday we had a clear understanding of the elastic materials, right? Mechanical properties, elastic material. You put in stress or you put in strain, you follow the stress over strain, modulus of velocity, no issues. This morning we did the viscosity measurement because shear stress over shear rate, clear thing in terms of the viscous component, viscosity of the material. Now we are going one step forward in terms of understanding the food material, trying to understand the viscoelastic nature of the material. And there is a way to analyze that through this process, where you can calculate the theoretical viscosity of your material. And this is the only way you can do it. You can make it a little more complex by adding additional spring and dashpot in your computation. But we don't have to do that far, We try to be as simple as possible, right? Or at least I like to be simple as possible because I am left-brainer. But there are classic examples where you can have multiple spring, multiple dash component and things like that. It's just a material. It's just a food material, right? So nothing more classic here. We don't even care about these things can happen for the material you are eating. It could be potato, it could be apple core. So at least you will appreciate next time you eat potato or apple core, these things can happen to your material. In fact, these things happening when you are eating it, right? Not to the same extent, but we don't know what extent these things happening for your food. You are eating and you digesting, you are swallowing, things like that. So that is why sensory analysis is also more complex. This can be, we cannot teach to everybody, right? And tell them these things and then ask them, okay, think about these when you are doing the analysis, things like that. They cannot, right? How much you can explain to them, how much you can train them so that they can understand all these things. Any other questions anybody has?
Sir, glass are known as pseudosolids because they do possess that flowability. So could we say glass have this theoretical velocity of infinite?
Oh, okay. Very good point. Your name, sir? Sagu, okay. Sagu, come to a point now, what we discussed yesterday. Yesterday I explained to you glass material also flows, even though it looks like it's stationary. Can we consider that glass is of this nature? Correct, it could be. Definitely it could be, right? We don't know how much elastic component, how much viscous component it has, but we know that glass material keep flowing. I mean, that's it. At least you can measure that, how much it flowed when you follow the process. Any material, every material flows for that matter. But at least in case of glass, you can really measure how much it flowed also. I mean, even wood also flows, right? Wood, but the issue here is wood not only flows, it can expand, it can contract. So it's complex thing. Everything is complex here. It's not as simple as what we think it is, right? It's complex thing. So glass can be considered, it has infinite viscosity because it's keep flowing, and it won't stop, right? Until we break it, and then that life is over. Then it cannot flow anymore. But if the glass is sitting there for thousands of years, it's what it is. Very good point, right? I mean, that's why I said you guys are all cream of the crop. Not everybody should think the same way, but individually you all think different, we all think differently. So we try to connect things. Okay, so when we leave after this session, when you go to practical session, you are going to look at the both the texture analyzer or compression test machine and also the rheometer, and you are going to observe the different phenomena what we talked so far. I'm not sure whether how much we are going to show them the viscoelastic thing. We are going to do the viscosity measurement, yeah, and then we are going to do the elastic compression test and TPA. Okay. Is this answer your question, ma'am? This morning you asked about applying stress and then observing strain. No, it's not yet. So we are going to do that after the practical session. I think in the morning you asked me about why we do constant stress experiment and then do the constant measure the constant strain.
For some different products, like for this product we should go with this model. Like with this heparin granule, for another product we should go for another system.
I am not sure about that is a case. My gut feeling is there are instruments, they are constant stress equipment, and there are instruments, there are constant strain equipments. But maybe some new instruments are coming up where you can do constant stress and then do constant strain. But that's something I need to look into that. I will come back to you sometime tomorrow on that one. So your rheology, your rheometer, you can do both. Can you do constant stress and then measure the strain?
We have done creep tests, sir. That's the constant strain one, but not the stress relaxation. We haven't done it yet. But creep test, yes, we have done. Constant stress we have kept and measured the strain parameters. Yes, we have done.
But can you still do the constant strain and then monitor the stress relaxation?
We haven't done it.
Can you do that in your rheometer?
I think we can do. But we
Can you look into that
yes,
so that we can come back and answer her question?
sure.
I doubt it. I don't think you can do that.
Because from my knowledge I am telling, for creep, whatever we have seen is like I have looked into dough, where we can see viscoelastic behavior of dough. But for stress relaxation, usually we will be doing tensile test. For example, in films, where the probe will we apply a constant stress and the film will break out. So we get a graph of for stress relaxation.
No, I understand. But the question here is what Nivedita is saying, that is they have done creep test, which is the constant strain, constant stress, and then you follow the strain, deformation. They have done it with the rheometer. But she is also saying that you can do relaxation by doing the tensile test for the same sample for the films, but that will be in a different instrument, not in this instrument, right?
My opinion.
Yeah, exactly. So I'm going back to my original thing. I'm not sure you can do in the same instrument both the thing. Please check it out. I will also check it out one more time because I don't want I do not know everything, right? Obviously, that cannot be happening. So I will find it out whether that can be done in the same instrument. I have to do some checking. Meantime, check on your instrument whether you can do relaxation in your experiment, in your instrument. Okay. You can do stress relaxation experiment in the textural analyzer. Okay, you can do constant deformation and follow the stress relaxation. You can do that, I know that. You cannot do the creep test in the same instrument. Creep has to be done on a separate experimental setup. If you don't have the rheometer, you can do it like this. You can take a sample, one of the sample core of your sample. You can apply the constant force there, and monitor the deformation. That is creep, right? That cannot be done in the compression test machine or texture analyzer. You cannot do that. There is no provision for that, because you cannot measure the deformation. You cannot physically measure the deformation when you apply the constant stress. Constant stress has to happen standalone. When you go back to the lab, I will explain to you. You will know little. You will clearly understand. I hope you will clearly understand what's the difference between what I talked about now, what your texture analysis is going to do for you. Thank you.